Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is non-ideal transformers. Our objective is to examine the efficiency of non-ideal transformers. We'll examine copper and two types of iron losses. Additionally, we'll discuss magnetizing or excitation current, and finally we'll examine transformer voltage regulation for a range of load requirements. This lecture operates under the presumption the viewer has more than a passing familiarity with transformers and is comfortable with performing series parallel AC circuit analysis. If you lack this level of familiarity, by all means review and revisit the contents of the AC circuit analysis playlist. Recalling the Introduction to Transformers lecture, available at the Big Bad Tech channel, we operated under the somewhat dubious presumption that transformers are 100% efficient devices, and all power input to the transformer is transferred to the output with no losses. This is obviously a lie. However, not one of gargantuan proportions. Transformers, even poorly made ones, are astoundingly efficient devices, principally because they're composed of no moving parts. This being said, they're not perfect, and we sometimes need to account for these slight imperfections using different models of non-ideal transformers. It's worth noting these approximations of non-ideal transformers are simple models at best, and are not high-fidelity approximations. This being said, they're pretty good. The minor imperfections of a transformer are generally lumped into a couple categories: copper losses, two types of iron losses, and the necessity of additional magnetizing or excitation current beyond that attributable to electrical load demands. Let's deal with these non-ideal behaviors one by one. Copper losses are those losses attributed to the small yet measurable resistance of the copper windings, hence the name copper losses, comprising the transformer. Given the windings of a non-ideal transformer have resistance, small though it may be, we might expect them to heat up slightly and a small portion of power input to the transformer to not be transferred to the output, but rather lost as heat. To keep copper losses to a minimum, a high-efficiency transformer would use thicker, more conductive wire. However, this transformer would be heavier and more expensive as a result. While we're on the subject of wires, it should be noted that a transformer primary and secondary windings are electrically insulated from one another. These windings are electrically insulated from the core, and the wires within the same winding are electrically insulated from other wires in that same winding. In order to keep cost and weight to a minimum, these wires are ordinarily not coated in plastic insulation, but rather a thin, electrically non-conductive varnish. This varnish, while cost-effective, can wear out over time, especially for a transformer that carries a large amount of current or is routinely overheated. A loss of this insulating varnish is often the principal reason for transformer failure. Moving on, the two types of iron losses are those losses associated with different aspects of the magnetic transfer of power through the iron core of the transformer, hence the name iron losses. Recall that transformers operate under the principle of electromagnetic induction, where AC current flowing in the primary winding creates a changing magnetic field. This changing magnetic field is then confined to a magnetically permeable iron core, magnetically linking the primary and secondary winding, and a voltage potential is induced across the secondary winding proportional to the rate of change of the magnetic field and the number of turns in the wire loop. An ideal transformer assumes the iron core is a perfect conduit for the changing magnetic field and does not in any way influence power transfer. This isn't entirely true for two reasons, one being hysteresis, the other being eddy currents. I like to think of hysteresis as the magnetic equivalent of the set and reset values for a switch, meaning something like a pressure switch will activate at a certain pressure when pressure is rising, however deactivate at a different pressure when pressure is falling. In this sense, hysteresis can be thought of as a kind of magnetic sluggishness of the material, where the material, having been magnetized with a given polarity and settled in for the night, is somewhat reluctant to get out of bed and realign itself again. Iron hysteresis losses imply that the transformer may necessitate a slight push to overcome this reluctance. Keep hysteresis losses to a minimum, high-efficiency transformers are sometimes conducted with exotic, i.e. expensive, core materials other than iron. Eddy currents are also considered iron losses, but of another form. Given the iron core is composed of a conductive material and is entirely inside a changing magnetic field, might there not be an induced potential and result in current flow within the iron core itself? Indeed there would. These inadvertently induced currents are known as eddy currents, and like the boils of a turbulently moving liquid, don't really go anywhere, but rather churn about and make it generally harder for the system to operate smoothly. These eddy currents inside the resistive core also result in power losses in the form of heat. To keep eddy current iron losses to a minimum, transformers often utilize not a solid iron core, but rather a stack of laminated sheets of iron electrically isolated from one another. These stacked sheets of magnetically permeable material still confine and focus the magnetic field. However, any current inadvertently generated during this process is now confined to a smaller region, and as such results in less heat generated and less power lost. Finally, given a transformer requires magnetism to operate, it stands to conjecture that it may necessitate the consumption of a certain amount of reactive power to accomplish this task. Recall that reactive power is the cyclical exchange of power between the source and a circuit necessary for the proper operation of reactive components like capacitors and inductors. This different dimension of power can be accounted for as an additional amount of current called the magnetizing or excitation current drawn in excess of load requirements. Additionally, we'll learn that transformers, even those not supplying power to a load on the secondary, always draw current, and as such, might exhibit losses even in the standby mode. In summary, copper losses explain transformer inefficiencies due to small but measurable winding resistance. Iron losses account for losses in the magnetic transfer of power due to hysteresis and eddy currents. And finally, magnetizing or excitation current accounts for the reactive nature of a transformer. Let's see if we can come up with a workable model for a transformer accounting for these realities. Consider a perfectly ideal 5-to-1 step-down transformer powered by 120 volts AC, providing current to a purely resistive load of, let's say, 10 ohms. Given our turns ratio is 5-to-1 and voltage is directly proportional to turns ratio, our given values suggest that the secondary output of this transformer will be 1/5 of 120 volts, or 24 volts. Let's say the rated voltage of the secondary winding is 24 volts and the rated current is 5 amps, meaning the secondary winding has a 24 times 5 or 120 volt amp rating. Given an equally rated primary, our primary winding would have a rated voltage of 120 volts and a rated current of 1 amp, meaning that the primary winding also has a 120 volt amp rating. Let's first perform an analysis of the secondary output. When 24 volts is applied to a 10 ohm resistive load, Ohm's law demonstrates that the current through it will be 2.4 amps at an angle of 0 degrees. Given these conditions, the power equation demonstrates that the load will consume 57.6 volt amperes of apparent power, all of which is being directed towards 57.6 watts of real power, and none of it towards a reactive interchange. This is well inside the operational range of the secondary winding's rated current and rated power. Let's now examine the primary input side of the transformer. There's a couple methods of doing so, although for the purposes of this particular lecture, it's perhaps easiest to use the reflected impedance seen by the primary winding. The turns ratio squared times the load impedance demonstrates that the source would see a reflected impedance of 250 ohms at an angle of 0 degrees. Ohm's law demonstrates that the primary winding will draw 480 milliamperes at an angle of 0 degrees. Given these conditions, the power equation demonstrates that the transformer is consuming 57.6 volt amperes of apparent power, all of which is being directed towards 57.6 watts of real power, and none of it towards a reactive interchange. In this ideal scenario, we're observing a condition in which power in does indeed equal power out, and no losses are observed. This is obviously too good to be true. However, let's use these figures as a basis of comparison. In the previous analysis, we assumed the source supplying the current to an ideal transformer saw only the reflected impedance equal to the load impedance times the turns ratio squared. Given magnetism is essential to the operation of a transformer, it stands to conjecture that the source might see something more than the reflected impedance, principally the reactive portions of the windings comprising the transformer. Various models account for the reactance of transformer windings. Perhaps the simplest model we can employ is to imagine an ideal 5-to-1 transformer, only this time including a large inductor, Z-mag, in parallel with a primary. The large inductor Z-mag is meant to account for both magnetizing current and hysteresis associated with non-ideal transformers. More accurate models might account for these two non-ideal properties separately. However, let's lump them together in a single inductor for the sake of simplicity. Let's assume the inductor accounting for both magnetizing current and hysteresis has a fixed magnitude of 2 kiloohms at an angle of 90 degrees at this particular excitation frequency. Since we haven't messed with the secondary side yet, the 10 ohm resistive load still experiences 24 volts and Ohm's law demonstrates the current through it will be 2.4 amps at an angle of 0 degrees. Given these conditions, the power equation demonstrates the load still consumes 57.6 volt amps of apparent power, all of which is being directed towards 57.6 watts of real power, and none of it towards a reactive interchange. Let's now examine the primary input side of the transformer. This is where things begin to diverge from our ideal expectations. As previously, let's perform this analysis using the reflected impedance seen by the primary winding. The source still sees a reflected impedance of 250 ohms at an angle of 0 degrees. However, this time the reflected impedance is seen in parallel with a 2 kΩ at an angle of 90-degree inductor. This additional current path will undoubtedly draw more current from the source. This being said, the inductor accounting for both magnetizing current and hysteresis is assumed to be entirely reactive in nature and will not consume any real power, but rather cyclically exchange it with the source. Given voltage across elements in parallel is the same, both the reflected impedance and inductor will experience a 120 volt differential. Ohm's law demonstrates that the reflected impedance will still draw 480 mA of current at 0 degrees. Ohm's law additionally demonstrates that the 2 kΩ inductor, accounting for both magnetizing current and hysteresis, will draw 60 mA of current at an angle of negative 90 degrees. Kirchhoff's current law demonstrates that the current in the primary will be 480 mA at an angle of 0, plus 60 mA at an angle of negative 90 degrees, or roughly 483.7 mA at an angle of negative 7.1 degrees. As we anticipated, source current increased because of the additional path in parallel. Additionally, note current in the primary is now slightly lagging supply voltage since we've included a reactive element in our model. Let's now examine power. The power equation demonstrates the reflected impedance will still consume 57.6 volt amperes of apparent power, all of which is being directed towards 57.6 watts of real power, and none of it towards a reactive interchange. The power equation additionally demonstrates the inductor accounting for both magnetizing current and hysteresis will consume 7.2 volt amperes of apparent power, none of which is being directed towards real power, and all positive 7.2 VARs is being directed towards a reactive interchange. There's a couple ways of calculating total apparent power input to the transformer. First, total power is the sum of the individual apparent powers. Additionally, total apparent power is the complex conjugate of primary voltage times primary current. Either method yields a total apparent power input of approximately 58 volt amperes, 57.6 watts of which goes to the reflected impedance, and positive 7.2 VARs of which goes to the inductor accounting for both magnetizing current and hysteresis. Let's now examine efficiency. As we anticipated, the inductor accounting for both magnetizing current and hysteresis draws more current. However, it consumes only reactive power and doesn't interfere with the transfer of real power. Real power in does indeed equal real power out, and our transformer can still be considered 100% efficient. In summary, this slightly more sophisticated transformer model accounted for a slight increase and a slight lag in source current one might observe for a non-ideal transformer when magnetizing current and hysteresis are taken into consideration. Additionally, we observed the transformer necessitated the consumption of a small amount of reactive power. This being said, the differences are pretty small, and the total amount of real power supplied to this transformer is indeed being totally consumed by the load. Efficiency with respect to real power remains 100%. The relatively small 7.2 VARs of reactive power simply accounts for the reactive nature of the transformer windings. Let's step this up a notch and see if we can account for iron losses associated with eddy currents. Perhaps the simplest model we could employ is to include a large resistor in parallel with the inductor accounting for both magnetizing current and hysteresis and the primary windings of an ideal transformer. Let's assume the resistor accounting for iron losses associated with eddy currents, ZFE, has a magnitude of 8 kiloohms. Since we haven't messed with the secondary side just yet, the 10 ohm resistive load still experiences 24 volt differential, and Ohm's law demonstrates that the current through it will be 2.4 amps at an angle of 0 degrees. Given these conditions, the power equation demonstrates the load still consumes 57.6 volt amperes of apparent power, all of which is being directed towards 57.6 watts of real power, and none of it towards a reactive interchange. As previously, let's now analyze the primary input side of the transformer using the reflected impedance seen by the primary winding. Given we've included yet another leakage path in parallel with the reflected impedance, we might expect this model's behavior to increasingly diverge from our ideal expectations. This additional current path in parallel will undoubtedly draw more current from the source, only this time, the additional current path is resistive in nature and can be expected to consume an amount of real power considered a loss. Let's see if this is the case. Given voltage across elements in parallel is the same, the reflected impedance, the inductor accounting for magnetizing current and hysteresis, and the resistor accounting for iron losses associated with eddy currents will all experience a 120 volt differential. Ohm's law demonstrates that the reflected impedance will draw 480 milliamperes of current at an angle of 0 degrees. The 2 kilo ohm inductor will draw 60 milliamperes of current at an angle of negative 90 degrees, and the 8 kilo ohm resistor will draw 15 milliamperes of current at an angle of 0 degrees. Kirchhoff's current law demonstrates that the current in the primary will be 480 milliamperes at an angle of 0 degrees, plus 60 milliamperes at an angle of negative 90 degrees, plus 15 milliamperes at an angle of 0 degrees, or roughly 498.6 milliamperes at an angle of negative 6.9 degrees. Source current again increased because of the additional path in parallel. Now let's examine apparent power for the individual elements in this model. The power equation demonstrates the reflected impedance will still consume 57.6 volt amperes of apparent power, all of which is being directed towards 57.6 watts of real power, and none of it towards a reactive interchange. The power equation additionally demonstrates the inductor accounting for both magnetizing current and hysteresis will still consume 7.2 volt amperes of apparent power, none of which is being directed towards real power, and all positive 7.2 VARs is being directed towards a reactive interchange. Finally, the power equation demonstrates that the resistance accounting for iron losses associated with eddy currents will consume 1.8 volt amperes of apparent power, all of which is being directed towards 1.8 watts of real power, and none of it towards a reactive interchange. This would be considered a loss to this system. There's a couple ways of calculating total apparent power input to this transformer. First, total power is the sum of individual apparent powers. Additionally, total apparent power is the complex conjugate of primary voltage times primary current. Either method yields a total apparent power input of approximately 59.8 volt amperes, 57.6 watts of which goes to the reflected impedance, 7.2 VARs of which goes to the inductor accounting for both magnetizing current and hysteresis, and an additional 1.8 watts goes to iron losses associated with eddy currents. As we anticipated, the resistor accounting for iron losses associated with eddy currents consumed a small amount of real power that's considered a loss to this system. As such, we might expect it to take a hit on efficiency. Real power input to this transformer is 59.4 watts. Real power out is 57.6 watts. Accounting for iron losses associated with eddy currents, this transformer can now be said to be 57.6 over 59.4, or only 96.7% efficient. We're not really 100% efficient. However, we might as well be given such small losses. This non-ideal transformer would dissipate these small losses as heat, and as such might exhibit a small temperature rise. Let's again step this up a notch and see if we can now account for copper losses associated with the resistance of the transformer windings. This time, we need to modify both the primary and secondary side, and as such, we'll need to perform a more involved series parallel circuit analysis. Let's say the secondary winding can be modeled as having a small resistance, ZCU2, of 0.25 ohms in series with the 10 ohm load resistance. Similarly, let's say that the primary winding can be modeled as having a slightly larger internal resistance, CCU1, of 1 ohm in series with a parallel combination of the resistor accounting for iron losses associated with eddy currents, the inductor accounting for both magnetizing current and hysteresis, and the primary winding of an ideal 5-to-1 step-down transformer. You note the internal resistance of the low voltage secondary winding of this step-down transformer is less than that of the high voltage primary winding. This is to be expected. Given the low voltage winding is expected to carry high current, one would ordinarily construct this winding using less turns of thicker, more conductive wire that exhibits a smaller internal resistance. Similarly, given the high voltage winding is expected to carry less current, one would construct this winding out of more turns of thinner, less conductive wire that exhibits a slightly higher internal resistance. Given we've included a series resistances in both windings, we might expect these resistances to drop a small amount of voltage and as such dissipate a slight amount of power considered a loss to our larger system. Let's see if this is the case. Using this more complicated model, it necessitates a slightly more advanced series parallel analysis. Let's use the reflected impedance seen by the primary winding. Given load impedance is now in series with the internal resistance of the secondary winding, the primary sees an additional reflected impedance of the turns ratio squared times the series combination of the load impedance and the internal resistance of the secondary winding. In this scenario, the reflected impedance is 5 squared times 10.25, or 256.25 ohms at an angle of 0 degrees. This reflected impedance is in parallel with the 8 kΩ resistor accounting for iron losses associated with eddy currents, and the 2 kΩ inductor accounting for both magnetizing current and hysteresis. Taking these three elements in parallel results in a combined impedance of approximately 246.4 ohms at an angle of 7.1 degrees. Let's call this combined impedance ZX. The 1 ohm internal resistance of the primary windings is in series with a combined impedance ZX. Given the relative magnitudes of these two series impedances, one might expect a majority, but not all, of the voltage to be dropped across the combined impedance ZX. Using the voltage divider rule, it can be demonstrated that the combined impedance ZX will experience a voltage drop of approximately 119.5 volts at an angle of 0 degrees. As we anticipated, a majority of the applied voltage is dropped across the combined impedance ZX. For those following along with these calculations, note that there will be an extremely small, almost negligible phase shift of 0.029 degrees, essentially 0 degrees. Similarly, using the voltage divider rule or Kirchhoff's voltage law, it can be demonstrated that the internal resistance of the primary windings will experience a voltage drop of approximately 485.0 millivolts at an angle of -7 degrees, less than half a volt. As we anticipated, the internal resistance of the primary windings does experience a voltage drop. However, not very much. This being said, it will still dissipate a small amount of real power considered a loss to the system. More importantly, the inclusion of this series resistance accounting for the internal resistance of the primary windings demonstrates that not the full 120 volts, but rather only 119.5 volts will be applied to the reflected impedance. You'd think a reduction of only half a volt wouldn't be that big of a deal, but as we'll learn in a moment, this will have a noticeable effect on power transfer. Recall that the combined impedance ZX is the parallel combination of the resistor accounting for iron losses associated with eddy currents, the inductor accounting for both magnetizing current and hysteresis, and the reflected impedance. Given voltage across elements in parallel is the same, these three elements, the reflected impedance, the inductor accounting for magnetizing current and hysteresis, and the resistor accounting for iron losses associated with eddy currents, will all experience a voltage differential of approximately 119.5 volts at an angle of 0 degrees. Ohm's law demonstrates that the reflected impedance will draw approximately 466.4 milliamperes of current at an angle of 0 degrees. The 2 kΩ inductor will draw approximately 59.8 milliamperes of current at an angle of -90 degrees, and the 8 kΩ resistor will draw approximately 14.9 milliamperes of current at an angle of 0 degrees. You'll note, because of the smaller applied voltage, the reflected impedance is now drawing less current than our previous simplified models. This will have a notable effect on power transfer to the load on the secondary. We'll examine this in a moment after we've finished the analysis of the primary side. Kirchhoff's current law demonstrates that the primary current will be I single prime plus I mag plus IFE, or roughly 485.0 milliamperes at an angle of -7 degrees. Let's now examine power for the individual elements in this model.